The LTM 1750, a mobile telescopic crane without equal. The construction site Colossus can lift incredibly heavy loads and transport them to dizzying heights, even over buildings. Despite its enormous weight, this mobile telescopic crane made in Germany can get to its worksite by road. And it's extremely maneuverable for its length and width. The construction of this behemoth is a masterpiece of German engineering. Engines developed in-house, huge telescopic booms, and a whole load of high tech. Ehingen in Baden-Württemberg, Germany. The cityscape is dominated by the Liebherr factory. The family company is the global market leader in the mobile and crawler crane sector. Around 30,000 of the German manufacturer's mobile cranes are currently in service around the world. On a site covering nearly 1 million square meters, a quarter of which is filled with production halls, roughly 4,000 workers build 6 mobile or crawler cranes each day. King of the lattice boom crawler cranes is the LR13000, the largest mobile crane in the world with a maximum load capacity of 3,000 tons. It can even maneuver on site with a load on the hook. Another much more frequently requested record holder is the LTM 1750 mobile telescopic crane. It's the largest mobile crane in the world that can drive on the road with its enormous telescopic boom mounted. The 108-ton gross weight of the LTM 1750 is spread over 9 axles, which equates to 12 tons per axle, the maximum permissible axle load. The wheeled steel Colossus is 22 meters long, 3 meters 90 high, and 3 meters wide. 4 of the crane's axles are driven, and all 9 are steerable. The LTM 1750 can lift up to a maximum of 800 tons with its 52-meter telescopic boom. With the lattice jib attached, its maximum lift height is increased to 152 meters. The load the crane can lift depends on the operating radius. Even at the maximum 160 meters, it can still lift 1.8 tons. The basic version of the LTM 1750 costs approximately 4 million euros. It essentially consists of 4 elements. The carrier, including outriggers. The superstructure, consisting of the rotating platform and power pack, the engine used for operating the crane and the telescopic boom. The metal fabrication shop at the Ehingen factory. This is where the frame sections for the mobile telescopic crane are made. They consist of over 1,000 individual parts that all have to be joined together exactly according to the fabrication plan, a job that requires precision work from the welders. Once a part is in the right position, it's provisionally fixed with tack welds. Only afterwards is the actual seam welding performed. At this machining station, the finished mid and rear section of the carrier chassis are upside down. Threads are cut into the milled bearing surface for the rotating superstructure of the crane. The 7.1-ton frame of the rotating platform, fresh from the fabrication shop. In order to install the first component, the assembly workers have to turn the massive structure upside down. The rotating platform is part of the crane superstructure, which supports the telescopic boom at the front and the power pack and counterweights at the back. The slewing ring forms the connection between the rotating platform and carrier. It allows the crane superstructure to rotate 360 degrees when in operation. The assembly workers now have to attach the slewing ring to the rotating platform. In order to get it aligned just right, they screw centering pins into holes in the rotating platform. Located on the centering pins, the slewing ring, which is also referred to as a slewing bearing, is attached to the superstructure using 300 bolts.
The roller bearing slewing ring we see here consists of an inner ring and an outer ring. The inner ring is bolted to the superstructure, which is on its back here, and the outer ring will later be bolted to the carrier. There are roller bearings between the inner and outer rings that allow the outer ring to rotate around the inner ring.
The mechanics run the hoses for the hydraulic system along the frame of the already primed carrier and install electrically controlled hydraulic valve modules. The carrier is basically the chassis of the LTM 1750, with driver's cab, engine, outriggers, axles, and wheels. The mobile telescopic crane is equipped with hydraulic axle suspension. Mechanic Maximilian Schulz has to install some crucial components for it, the so-called hydraulic accumulators.
Später sitzt hier in der Mitte.
The axle will later sit in the middle here.
Die Achse wird gestützt von
The axle is supported by two hydraulic shock absorbers, one on each side.
Die sind mit Hydrauliköl
They're filled with hydraulic oil,
Dafür noch,
and they need hydraulic accumulators to
Im
work.
hinteren Teil durch eine Membran.
The rear section is filled with nitrogen at a pressure of 35 bar,
Bei dieser Membran ist es 35 bar.
which is kept separate from the oil by a membrane.
Hydraulikstoßdämpfer verdrängt.
If the crane drives over a pothole, for instance,
Wird das
oil is displaced from the hydraulic shock absorber,
dem ganzen Hydrauliksystem
which will
verdrängt
later be connected to the rest of the hydraulic system here
und wird
and is forced
dann
into the hydraulic accumulator.
Die Membran
The membrane gets forced backward, compressing the nitrogen and thus absorbing the impact from the shocks.
von den Hydraulikstoßdämpfern wird somit abgefedert.
The mechanics have to connect 18 such hydraulic accumulators to the hydraulic suspension system, 2 per axle. The power pack is part of the superstructure. It's basically the engine for operating the crane. Its 435 horsepower 6-cylinder diesel engine powers hydraulic motors and pumps to operate the cable winches and generates oil pressure for raising, lowering, and extending the telescopic boom and turning the rotating superstructure. The power pack weighs a hefty 16.1 tons, which is why it can only be installed once the crane has reached the job site. It sits between the counterweights and lifts up the entire ballast tray, that is, the crane's counterweight. The raising operation is performed by these ballast cylinders. They're 2.3 meters long and weigh 2.6 tons each. Assembly workers Thomas Clay and Alexander Ha now mount them onto the power pack. They have to take great care when sliding them into the mounting points to avoid causing any damage. This 70-kilo pin locks the ballast cylinder in place during transport and after picking up the ballast tray. Finally, the mechanics tighten the ballast cylinder retaining bolts with a torque of 1,600 Newton meters. The hydraulic unit supplies the required pressure of 284 bar. In the large crane facility, the mechanics are finishing installing the mobile telescopic crane's running gear. Manuel Zen and Lukas Schweikert lift the final axle into place. It's a non-driven axle that only weighs 1 ton. The 4 driven axles weigh 1.5 tons each. The axle is now at the right height. The men fasten the axle struts to the axle mounting points on the carrier. These adjustable axle struts ensure that the distance between the axles remains exactly the same. This is important for tracking, steering, and power transmission. The next job, attaching the hydraulic suspension cylinders to the axle. The mechanics slowly lower the axle, tap in the axle pins, and secure them. Next up is the steering system, installation of the steering rod.
There's a mechanical connection to the first axle, and the steering is hydraulically assisted. A purely mechanical system would be impossible. You can see the cylinder up here. That's the hydraulic assistance, like the power steering on a car.
The steering linkages are connected via bell cranks to axle 5. The rear axles are controlled by another steering system.
The remaining 4 axles are steered electro-hydraulically via hydraulic manifolds. Axles 6 and 7 via these manifolds here, and axles 8 and 9 via the manifolds at the back.
The 2 independent systems allow the LTM 1750 to steer the rear wheels in a different direction to the front wheels. This makes the mobile telescopic crane extremely maneuverable. A big advantage in city traffic, like here in Cologne, and for entering difficult-to-access construction sites. When at the job site, it's able to maneuver well, even where space is limited. The manufacturer also adopts a dual approach when it comes to the braking systems.
All of the axles are equipped with disc brakes, and there's an eddy current brake fitted to axle 6 as well. The eddy current brake generates a magnetic field that acts on the drivetrain while causing minimal wear. This is the preferred system as it increases the life of the disc brakes.
Once the drive shafts are fitted, the workers must turn the carrier the right way up again. To do this, the mechanics have attached a motor suspended from a crane hook to the rear of the carrier. The second device required for turning the carrier over is this giant wheel. The mechanics place the 3.9-ton rotating device directly in front of the carrier. Manuel Zen and Lukas Schweikert now raise the carrier, which now weighs 23.3 tons. They then maneuver it into the rotating device and secure it. Now Lukas Schweikert just has to detach the chains from the front of the carrier. Then the rotating process can begin. The rotating platform, which will later sit on top of the carrier, is almost finished. Electricians and mechanics run the last of the connections for the cab, from where the crane will be controlled when on site. The mechanics are almost finished running the connections to the carrier. The lines pass through the slewing ring, which will be bolted to the carrier during final assembly. The rotating platform has a cable winch, but no engine of its own.
A special feature of this crane is that the superstructure engine is not installed on the rotating platform, but in the power pack. Because the power pack is transported separately to the job site by truck, the crane has to rig itself.
Like here at a construction site near Flensburg, the LTM 1750, with its maximum permitted gross weight of 108 tons, has already maneuvered into the correct position and extended its front outriggers. First, the 2-ton load block through which the hoist cable runs must be mounted. Then, the mobile telescopic crane attaches the rear outriggers, which weigh 4.5 tons each. Once extended, the crane no longer rests on its wheels, but is supported solely by the 4 outriggers. Now the crane operator can place the 11-ton ballast tray on the carrier of the mobile crane. Additional counterweights are then loaded onto this tray. The LTM 1750 can accept a maximum of 204 tons of ballast. Now, the rotating platform engine, the power pack, arrives by truck. It weighs a massive 23 tons. The crane operator sets it down behind the rotating platform between the counterweights. Only when the power pack, also known as the primary aggregate, has been installed, can the LTM 1750 operate at full power. The fact that the crane was able to rig itself, even without the power pack installed, is thanks to an important component of the rotating platform.
This is the secondary aggregate, the so-called hydraulic shaft. There's a pump fitted to the carrier engine. It transmits pressure up to the rotating platform, feeding the hydraulic motor that serves the entire pump circuit. This allows the crane to perform all movements without the power pack, just at a reduced speed and naturally with reduced power.
The blanks for the telescopic boom are supplied by subcontractors. The workers in this shop turn the pre-primed tubes into finished booms. They consist of an outer section, known as the boom base, and 3 telescoping sections. Andreas Gauss and Mario Krite are currently working on a boom for the LTM 1750, specifically on the boom tip. The industrial mechanics fit the head and neck sheaves made from a special plastic. The hoist cable will later run over these sheaves. The more sheaves, the less power the crane needs to raise a load. It's the same principle used by the overhead cranes at the factory. At the base of the telescoping section, the industrial mechanics now have to install a locking mechanism. First, so that it shrinks, a bushing has to be cooled down to -196 degrees Celsius in liquid argon, a noble gas. Andreas Gauss places it into a bore. When the bushing warms up to ambient temperature, it expands and sits securely in place. A steel spring is then placed into the bore, followed by the 70-kilo locking pin, which has a mushroom head on the bottom end. Finally, the locking mechanism is bolted to the telescoping section. A mobile crane that weighs in excess of 100 tons needs a massive engine to power it. The LTM 1750 is equipped with a V8 diesel built in-house by the crane manufacturer. The 16-liter engine produces 680 horsepower.
Attached to the Liebherr engine is an automatic transmission from ZF. And above it are the hydraulic pumps for the steering, outriggers, suspension and ventilation systems.
Lifting the 2.5-ton unit into place is a tricky job. Mechanic Maximilian Schulz gives instructions from above, while his colleague Daniel Kloka operates the overhead crane.
A little bit higher. Then we'll turn it. Okay, that's enough. We probably have to move it a bit further forward.
The mechanics have to precisely line the engine up with mounting points while making sure that no hoses or cables get trapped. 10 minutes later, the engine is in the right position and the mechanics can lower it. Maximilian Schulz and Daniel Kloka now position the engine so that it sits exactly in the center of the chassis. To do this, they suspend a plumb line from the center of the engine and measure the distance on the left and right to the frame. 1 centimeter difference.
That's good.
If the engine wasn't located just right, the mobile crane's center of gravity wouldn't be exactly in the middle, and it wouldn't be possible to connect the universal joint of the drive shaft either. The drive shaft powers 4 of the 9 axles via transfer cases, but attaching it to the gearbox turns out to be difficult.
I'll go down and turn the drive shaft.
Okay.
The holes in the drive shaft don't match up. I need to turn the other drive shaft so this one up here lines up. Keep going, a bit further in this direction. Yeah, further. Okay, stop there. It's good.
The drive shaft can finally be bolted to the gearbox. The next task for Maximilian Schulz and Daniel Kloka is installing the radiator. It's a combination radiator for the engine coolant, the hydraulic oil, the air conditioning system, and the charging air. Cold air contains more oxygen, which improves combustion of the air-diesel mixture in the engine. The mechanics first attach the air hoses for the air conditioning system and charging air, followed by those for the hydraulic oil and the engine coolant. Finally, they bolt the radiator to the carrier chassis. On the other side of the assembly facility, a marriage is about to take place. The 16-ton superstructure engine, that is, the power pack and auxiliary winch, is being coupled with the rotating platform. A job that requires good teamwork between Alexander Ha and Wilhelm Neth. The task is made easier thanks to some technical refinements. The power pack and rotating platform are fitted with automatic quick couplers for the hydraulic lines. And there are 2 locating pins on the rotating platform. They ensure that the hydraulic quick couplers slot exactly into one another.
Okay, moving forward now.
Okay.
Alex, is it lined up on your side?
Yep, looks good here.
The quick couplers make it unnecessary to connect the hydraulic lines by hand. This saves time when rigging the crane at the job site. All that's left is to insert the locking pins, and the marriage is complete. In the meantime, the 600-liter diesel tank and the hydraulic oil tank with a holding capacity of 300 liters have been installed on the carrier of the mobile telescopic crane and connected up. Some of the side panels have already been mounted too. But the biggest component is still missing, the driver's cab. It's nearly 3 meters wide and weighs about the same as a small car, 1 ton. With the driver's cab attached to the lifting beam, Maximilian Schulz and Daniel Kloka lift it onto the carrier chassis using the overhead crane. Before setting it down, they have to feed the connecting hoses and cables through the openings in the chassis, while making sure that nothing gets trapped. At the rear of the driver's cab, the mechanics mount it to the vehicle chassis using shock absorbers. These shock absorbers not only make it more comfortable for the crane driver, they protect the electronic components inside the cab from excessive vibrations. The mechanics then bolt the front of the driver's cab to the carrier chassis. Electrician Oliver Benz provides assistance with the next task. There are a multitude of cables that have to be fed through to power the instruments, electronic control units, and monitoring systems, as well as for the air conditioning system. Then there are the pneumatic lines for the foot brake, the emergency brake, and the parking brake. This process takes over 3 hours. Afterwards, Daniel Kloka installs another mechanical component, the steering linkage between the driver's cab and the running gear. The carrier is now more or less complete. The electrical and hydraulic components of the completed superstructure, that is, the rotating platform with coupled power pack, are now subjected to a variety of tests. These are performed by test technicians Thilo Edel and Ottmar Gösele. The components being scrutinized include the ballast cylinders on the power pack. When rigging the crane, they're used to raise the ballast tray with the ballast blocks from the carrier, so that the LTM 1750 has sufficient counterweight when performing a lift.
The first thing we need to do is start the engine so we can release the locking mechanism and extend the ballasting cylinders. Then we check the pressure during extension. If that's okay, we retract the ballasting cylinders again and check the pressure during retraction. It should be a maximum of around 300 bar. Okay, Ottmar, you can start the engine.
Before the actual test begins, Ottmar Gösele releases the locking cylinders. They ensure that the ballast cylinders remain in their current positions. Then the test technician extends the ballast cylinders. Thilo Edel checks the pressure of the hydraulic oil using manometers. It's okay, and the same on both sides.
Looks good here.
Now the test technicians retract the ballast cylinders. The oil pressure is checked once more. It isn't quite right. Thilo Edel adjusts it to the desired value. 300 bar. Everything's good. Once the locking pin is reinserted, the test is over. The two test technicians still have plenty of other tests to perform on the hydraulic systems and electronics. In order to test the carrier of the mobile crane, they first need to start the engine. The mechanics connect an exhaust gas extractor unit to the exhaust pipe. The diesel and hydraulic oil tanks have already been filled. The only thing still missing is the AdBlue, an aqueous urea solution used to reduce nitrogen oxide emissions. The tank of the LTM 1750 holds 60 liters. Now, Maximilian Schulz can start up the 680 horsepower diesel for the first time. Checking whether the engine runs smoothly and revs up evenly isn't the only purpose, though.
We have a number of test programs that put the whole carrier through its paces. We run through them one after the other. First up is the radiator fan test. We run the fan up to full power and check that there aren't any leaks.
The fan cools the engine coolant, the charge air for the diesel engine, the hydraulic oil, and runs the air conditioning system. None of the radiator connections are allowed to leak. Test passed. No leaks. Test number 2, the steering. Everything's okay here too. Next to be tested are the hydraulic oil pumps fitted to the carrier engine. They allow the crane to be operated in a limited capacity, even without the power pack, the Superstructure engine installed. This means the crane can rig itself at the job site and install the power pack without external assistance as well. Daniel Kroka connects a manometer. He uses it to check the pressure provided by the hydraulic oil pumps. A quick readjustment, and this test routine is also completed. Mounting the wheels of the mobile telescopic crane is not a job that can be done by hand, because each of the 18 wheels weighs 300 kilograms. But that's no problem for this special tire forklift. It enables mechanic Maximilian Schulz to fit the tires on the wheel hubs with ease. The enormous tires have a diameter of 1.5 meters and are mounted on 25-inch rims. They have a thread depth of 2.8 centimeters and are pumped up to a pressure of around 8 bar. Each wheel costs around 2,500 euros, so a complete set of all 9 axles adds up to roughly 45,000 euros. The 10 nuts on each wheel are tightened by machine. The powered torque wrench, which always tightens 2 nuts at a time, supplies the necessary 600 Newton meters. Thanks to these special machines, it takes 2 mechanics just 2 hours to fit all 18 wheels. The hoist cable of the mobile telescopic crane is 700 meters long and weighs 4 tons. Test mechanics Thilo Edel and Ottmar Gösele now have to spool the enormous hoist cable onto the Superstructure winch. To do this, they first mount the cable drum in a spooling jig. They attach the end of the 2.5 centimeter thick cable to the hook of an overhead crane and bring it to the winch installed on the rotating platform of the crane, to which it's then bolted.
So, das war's.
So, finished.
Sind die Schlüssel
Clamps are
angezogen?
tightened.
Müsste
Now
man
we have to go down and check the pre-tensioning.
und die Vorspannung anschauen.
The test technicians can't just spool the heavy cable onto the winch drum just like that. Ottmar Gösele first runs it over a pulley and raises it up using the overhead crane. Meanwhile, his colleague makes some other adjustments.
So, an der
Right.
Aufziehvorrichtung vom Seil
There's a brake on the spooling jig here that's pre-tensioned with a certain spring load to provide a braking force of around 500 kilograms.
so dass ich eine Bremskraft habe von ca. 500 Kilogramm.
When the brake is applied, the crane winch has to pull with a force of 5,000 newtons to keep the cable taut during spooling.
Die Seilvorspannung ist aus dem Grund
Pre-tensioning is important to ensure there isn't any loose cable on the drum, which could result in the winch getting damaged.
zu Schaden kommen kann an der Winde.
If the cable is too slack on the winch and we pick up a load, the load could suddenly drop down, causing damage to the cable.
Zu führen bei Aufnahme der Last,
And in the worst case, snapping it.
einen Schaden bekommt und im schlimmsten Fall auch reißt.
Thilo Edel's colleague Ottmar Gösele tensions the hoist cable by raising the pulley with the crane. He applies wax to the winch on the rotating platform. This helps prevent the steel cable from corroding. Thilo Edel starts up the winch on the superstructure of the crane. Spooling on the 700-meter-long hoist cable takes several hours. In the telescopic boom shop, the mechanics are preparing to slide the boom sections inside each other. Inside of this telescoping section has already been greased. Mechanic Andreas Gauss places slide plates made from a Teflon-like plastic at the ends. These banana plates prevent the slide plates from moving. Slide plates have already been installed at the bottom end of the telescoping section 2. The mechanics now slide this telescoping section into the next largest. Tele 3 has to go inside Tele 2. The men have to be careful when maneuvering the overhead crane to ensure that the 15-meter-long, 6-ton section doesn't start swinging. The mechanics continually check whether the telescoping section is sliding horizontally into the other or is in danger of twisting. Before Tele 3 can be completely inserted into Tele 2, the mechanics mount slide plates on the inside of Tele 2 and fix them in place with banana plates. The slings are removed, as they would get in the way when sliding the section the rest of the way in. The men now suspend Tele 3 from the chains at the back from the overhead crane and slide it all the way inside Tele 2. Once it's fully in, the boom pin springs out and locks Tele 3 inside Tele 2. Only when all the telescoping sections have been slid into one another can the mechanics install the telematic system. This hydraulic ram is responsible for extending the telescoping sections.
The telescoping ram is installed here. There are two cylinders here that fasten the respective telescoping section. Once it's fastened, this mushroom head is captured and pulled down by the yoke. At the other end of the mushroom head is a bolt. This bolt is released. In this way, the telescoping ram can extend the entire system to the desired length.
The carrier of the mobile telescopic crane is complete. The 4 hydraulic outriggers used when the crane is in operation have already been mounted and are now deployed. Everything is ready for the superstructure to be installed. It consists of the rotating platform and superstructure engine, the power pack. The massive structure weighs 26 tons. The men use 2 overhead cranes to transport it to the carrier.
We have to be careful when operating the overhead cranes, that we move slowly and in sync, or we could end up knocking into the shelving or other overhead cranes.
What follows is the trickiest part of the marriage, placing the superstructure onto the carrier. Because the holes in the slewing ring attached to the superstructure must line up exactly with the corresponding holes in the bearing surface of the carrier.
We use these templates to make sure that the holes in the rotating platform and carrier match up. By moving them around, we can find the right position of the holes in the bolt pattern. I can screw the centering pin in this position. We do the same up here on the rotating platform. You can see that the holes don't match up like this. I have to keep moving the template until I find the position where the holes align properly. This position is right, so I mark it with a pen.
The centering pin now has to go into the hole with the marking, a job that requires fine control of the overhead cranes.
Is it looking good on your side?
Yes.
A total of 388 wasted expansion screws are now placed in the holes. They're self-securing, which means they won't come loose, even under extreme stresses. Next, mechanic Alexander Corona makes the hydraulic connection between the carrier and superstructure. It's now possible to operate the crane even without the power pack, although in a limited capacity. Once the electronic control cables have been installed, the marriage between carrier and superstructure is complete. The 16-ton power pack must now be removed from the rotating platform again to make more space for completing assembly of the mobile crane. The enormous telescopic boom of the LTM 1750 mobile crane is on its way to the assembly facility. But before it can be mounted on the crane, Alexander Corona and Patrick Elmer first have to install the luffing cylinders on the rotating platform. Each cylinder weighs 2.5 tons. They're 6 meters long and have a diameter of 50 centimeters. When the crane is in operation, they raise and lower the telescopic boom. The mechanics have to work carefully when maneuvering the luffing cylinders into position to ensure that the 19-centimeter thick steel pins can be inserted and bolted into place afterwards. Once both luffing cylinders have been installed, they're connected to the hydraulic system. In order to raise the telescopic boom to an angle of 86 degrees, even under load, they require an enormous oil pressure of up to 400 bar.
This here is the cylinder connection. It regulates the pressure between the left and right cylinders so that they always operate the same.
If the pressure were different, it would overload one of the cylinders, resulting in catastrophic failure of the crane. Only one component required to complete the mobile crane is still missing, and it's the heaviest. The enormous telescopic boom weighs 35.7 tons. It's 16.3 meters long when retracted and 52 meters long extended. Patrick Elmer and Alexander Corona need two of the large overhead cranes in order to mount the huge structure. With their help, they maneuver the boom to the mobile crane. Three minutes later, the telescopic boom is at the mounting point on the rotating platform. The installation requires a delicate touch.
So we're now moving the boom into position. We have to get it exactly centered on the rotating platform. We need to set it down on the rails here and slide it back while adjusting the tip left and right to get the boom positioned precisely in the middle so we can get the pins in easily afterwards.
The locking pins have to go through these brass bushings. They have lubrication grooves machined in them that the men now brush with grease. Then the precision maneuvering with the crane remote controls begins.
Do you still have space?
A little, yes.
Okay, I'm touching.
I'm touching too.
Good, we can put the pins in.
Okay.
Pins of this size can't be inserted by hand though. It takes a special device and machine power.
Are we in already?
Yes.
Good. Okay, we're done.
Patrick Elmer and Alexander Corona now have to attach the luffing cylinder to the telescopic boom. Here too they apply grease to the brass bushings and locking pins. They use the overhead cranes to lift up the luffing cylinders. Then the pin insertion machine is used once more.
Good.
Are we in?
Done. Yep.
Once both of the pins have been inserted, they're secured with bolts. The mobile telescopic crane is fully assembled. Now it's time for the first of the function tests. From the operator's cab, industrial mechanic Patrick Elmer starts up the LTM 1750's engine. He performs the function test using the mobile crane's wireless remote control. First, he checks whether the luffing cylinders used to raise and lower the telescopic boom operate properly. Test number 2. The slewing motor, which must be able to rotate the superstructure through 360 degrees without jerking. The third and final test involves the crane's boom. Patrick Elmer checks whether it telescopes correctly. All of the systems work flawlessly, at least when not under load. Before being delivered to the customer, the LTM 1750 mobile telescopic crane spends 4 weeks at the enormous factory's testing ground, being put through its paces, namely in all configurations that the customer has ordered. For today's test, the technicians have loaded 204 tons of ballast and mounted an over 30-meter-long lattice luffing jib on the telescopic boom. They specifically want to check that the welds of the boom section hold even under maximum load. Before the test, Foreman Ralf Leichtle and test technician and crane operator Stefan Sauerbier discussed the plan.
I've attached the 31.5 lattice luffing jib.
Okay, we have to extend all the telescoping sections to 92% so we can load the luffing jib according to the test criteria.
Then I need to lift 49 tons.
Yes, that's right.
The test begins. The crane operator extends all 3 telescoping sections to 92%. The telescopic boom is now 49 meters long. Including the luffing jib, the total height of the crane is now 85 meters. Stefan Sauerbier takes up the strain with the hoist cable. The load on the hook steadily increases.
We're now at 20 tons, 30 tons. Now entering yellow zone. And we have shutdown.
The technical term is load moment limit.
That's the moment when the customer can't keep going, which means the load is too heavy. But because we're doing acceptance testing here, we can override it and push it to 130%. So we can test the crane thoroughly. I have to turn this key, then it blinks up here, and I can continue.
The option to override the system is reserved solely for the test technicians at the factory.
Okay, we've reached the test load of 49 tons, and the crane is still standing.
The test with the 31.5-meter luffing jib has been successfully completed. With longer lattice luffing jibs attached, the LTM 1750 mobile telescopic crane has a reach of nearly 120 meters. For this job in the Hamburg warehouse district, a 49-meter lattice luffing jib is attached. With it, the crane operator can lift a 38-ton sky bridge to its destination, over a multi-story building. The final test of the mobile telescopic crane concerns the handling characteristics of the LTM 1750. Fabian Stör tests the transmission, brakes, and steering program 1, for road use in particular. The slower the crane drives, the more axles are steered.
Now I'm switching to steering program 2. The crane has its smallest turning radius with this program.
During this maneuver, all 9 axles are steered. Steering program 3 is the so-called crab walk mode. All axles steer in the same direction. Steering program 4 allows the crane to drive while just turning the front wheels without the rear end swinging out. The result of the tests: all systems work perfectly. Now, the LTM 1750 just needs its final paint job. After that, the heavy lifter is ready to be delivered to the customer.